Hello everyone, welcome to Gate Pass. In this video, I am going to take problems that were related to thermodynamics and which appeared in GATE 2009 paper. So, the first problem, it talks about isothermal compression of an ideal gas in a closed system from temperature T1 and pressure P1 to final pressure P2 such that your final pressure P2 is greater than P1. They have given you four options and they have said that choose the correct one. Okay, so first of all, please notice that this is an ideal gas, and for an ideal gas, your internal energy is a function of temperature only. Since this is an isothermal compression, okay, so the temperature, initial and final temperatures are same. That means your initial and final internal energies should also remain the same. Okay, so in that case, you should have, since U is a function of temperature only, so then you should have U1 that is equal to U2. Okay, so that means my option C and D straight away are wrong. Now let's find out how G changes for this isothermal compression. So we know that change in G gives free energy, that is given as dG is equal to minus SdT plus VdP. Since temperature is held constant, this term will go to 0. So what I am left with is only VdP. Now I do not have any information about volume. So I will change the variable from V to T and P. And how I will do it? I will use my ideal gas law. So ideal gas law says that PV is equal to RT. If these are molar quantities, then I can write V that is equal to RT by P. So I am going to put dG that is equal to RT dP by P. Then I will integrate it from G1 to G2 and the pressure will change from P1 to P2. So after integrating, what you get is that G2 minus G1 that is equal to RT times ln of P2 by P1. Okay, since they have given that your P2 is greater than P1, that means this quantity over here, it will be greater than 0. And what it translates into? It translates into G2 minus G1 is greater than 0, or you can say that G2 is greater than G1. Okay, so G2 is greater than G1. Now let's see which option says this. G1 is greater than G2. No, this is wrong. For here it says that G1 is less than G2. Okay, so this option is correct. So your option B is correct. Okay, so the next question which I am going to take, it again involves compression of an ideal gas, but this time it is done adiabatically in a closed system. They have said that this gas is compressed from pressure 1 bar and temperature 300 Kelvin to a final pressure P2 and a final temperature T2 which is 600 Kelvin. Further, they have said that the efficiency, the mechanical efficiency of this process is 50%. Okay, and the value of Cp is 5 by 2R. Now they asked you to calculate what is the work required in order to compress this gas and the final pressure P2. Okay, so very straightforward problem. Again, for adiabatic compression, I am not going to use that big formula which is written in your book, in your textbook. I will go from the basics. Okay, so for this compression, because it is taking place in a closed system, I am going to write my first law which says that delta U is equal to Q plus W. Now my sign convention is that heat supplied to the system is positive and work done on the system is positive. Okay, now since this is an adiabatic process, Q is equal to 0, so my delta U is equal to W. Now for an ideal gas, I know the change in internal energy, it can be given as CV delta T. Okay, so work done can be directly calculated as CV times delta T. What is the change in temperature? So CV times T2 minus T1. Okay, that is my equation which I am going to use for calculation of work done, work which is required for a reversible process. First we will find this and then we will use the mechanical efficiency in order to calculate the actual work which will be required. So let's do that. Now Cp is given, but for ideal gas we know that Cp minus Cv is equal to R. Cp is 5 by 2R minus Cv that is equal to R, or I can find out CV, that is equal to 5 by 2R minus R, which comes out to be 3 by 2R. Okay. Now let's put our value of CV over here. So 3 by 2 times R, the value is given as 8.314. T2 minus T1, that is 600 minus 300. If you do the calculation, you will get the answer as 3741.3 joules per mole. Okay, but now the efficiency is given as 50%, so the work required will be equal to W upon efficiency. So I am going to divide this by 0.5. Okay, so that gives me my answer as 7482.6 joules per mole. Since they have asked you to calculate the work required in kilojoules per mole, so I will divide it by 1000 and write it as 7.48 kilojoules per mole. Okay, so this was the correct answer. So it's very simple. You do not have to use that big formula which is given in your textbook. You can still find very easily and very quickly your work done just by going through the basic equations which you have learnt. Okay, so next we will find out what is the final pressure. Okay, in order to find out the final pressure, what we will use is that for an adiabatic process, P1 V1 raised to gamma, that is equal to P2 V2 raised to gamma. Okay, or I can write that P1 by P2, that is equal to V2 by V1 raised to gamma. Okay, now since no information is given about the volumetric ratio V2 by V1, so I am going to change the variables from V to P and T, and for that I am going to use my ideal gas law. So I can write P1 V1 upon T1, that is equal to P2 V2 upon T2. Okay, now just solve this equation for V2 by V1. What you get is P1 upon P2, multiply it with T2 upon T1. Okay, now put this value over here. So what you get is P1 by P2 raised to gamma, multiply it with T2 by T1 raised to gamma. Okay, now let's take the pressure on this side, and what you get is P1 by P2. So it will be divided by this. So then it will be 1 minus gamma, that is equal to T2 by T1 raised to gamma. Okay, now let's since I want to solve for P2, what I will do is I will take a reciprocal of these two on both sides. So what I get is P2 by P1 raised to 1 minus gamma, that is equal to T1 by T2 raised to gamma. Okay, now I will solve for P2 by P1. So now this becomes P2 by P1, that is equal to T1 by T2, and if I take the power over there, so it will be gamma upon 1 minus gamma. Okay, or your P2 will be equal to P1 times T1 by T2 raised to gamma upon 1 minus gamma. Fine. We have now got an equation for P2. We know P1, T1 and T2. Let's find out what is gamma. So gamma is nothing but your Cp by Cv. Okay, Cp is 5 by 2R and Cv is 3 by 2R. Divide them, so you get 5 by 3. Now let's find out what will be gamma upon 1 minus gamma. So my gamma upon 1 minus gamma. So gamma is 5 by 3 divided by 1 minus 5 by 3. So it will be 5 by 3 divided by, so it will be 3 minus 5, so minus 2 by 3, or I have this as minus 5 by 2. Okay, so gamma upon 1 minus gamma is minus 5 by 2. I can write over here minus 5 by 2, or if I invert this, so I can write T2 by T1, and then I can take this as positive. Just mathematical manipulation, nothing else we are doing. Okay, so now your P1 is 1 bar, T2 is 600 Kelvin and T1 is 300. So T2 by T1 is 2. So your final pressure, that is equal to 2 raised to 5 by 2. Okay, so this is your final answer. So it was very simple. So the next problem which I am going to take, it involves a binary mixture at constant temperature and pressure. Okay, and it gives you following relations of gamma, which is your activity coefficient, as a function of your mole fractions. Okay, now they have said which of these values are thermodynamically consistent. Okay, so you have to first realize that your ln gamma I, it is a partial molar property with respect to GE by RT. So if this is a partial molar property, then it must satisfy your Gibbs-Duhem equation. How do I write my Gibbs-Duhem equation? I will write it as x1 d ln gamma 1 plus x2 d ln gamma 2, that should be equal to 0. In GATE 2021 paper, I have given you that you can also write this Gibbs-Duhem equation in another form, and that is x1 d ln gamma 1 by dx1 plus x2 d ln gamma 2 by dx1, that is equal to 0. Okay, you should go and check that video of GATE 2021, where from this equation I have derived this equation. Okay, so this is also a Gibbs-Duhem equation. Now since this is a partial molar property, then it must satisfy this equation. So what we will do is we will find out the derivative of ln gamma 1 and ln gamma 2 with respect to x1, and put those values in this equation and see which one of them equates to 0. The one which equates to 0 will be thermodynamically consistent. Okay, in order to reduce your mathematical efforts, realize this, that all the ln gamma 1 values are same, that is, it is minus 1 plus 2x1 minus x1 square. Okay, so first we will find out the value of your first term. Okay, so it will be x1 d ln gamma, so d by dx1 of ln gamma 1, it is minus 1 plus 2x1 minus x1 square. Take the derivative, so it is equal to 2 minus 2x1, or I can write this as 2x1 minus 2x1 square. Okay, so the first term in this equation, it becomes equal to 2x1 minus 2x1 square for all the 4 options. Okay, now quickly what we will do is we will find the derivative of these with respect to x1 and plug it over there and see whether it becomes equal to 0 or not. So for option 1, let's say it will be, so you have x2 d ln gamma 2 by dx1, so I am going to write, for x2 I am going to write 1 minus x1. Now take the derivative of this term, it will be 2x1 divided by 2, so it will be x1. So it will be x1 minus x1 square. Does this and this add up to make 0? No. So this option is out of question. Let's move on to the second option. Okay. So your second option is x1 square. If you take a derivative of this, it will be 2x1. So it will be, make it 2x1 minus 2x1 square. Okay, if I add it over there, then it will become 4x1 minus 4x1 square, so it doesn't make it to 0. So again, option B, it is not thermodynamically consistent. Okay, now let's take our third value. So derivative of this will be 2x, 2 will cancel, so it will be minus x1. So it will be minus x1 plus x1 square. Okay, now if I add it over here, so 2x1 minus x1 is x1 and minus x1 square. So again, it doesn't make this Gibbs-Duhem equation equal to 0. So this is also not thermodynamically consistent. Now let's see what is the final option. So we have minus x1 square, take a derivative of this, so it will be minus 2x1. So this will be minus, so this will be minus 2x1 plus 2x1 square. If I add it to this, so 2x1 minus 2x1, I'm going to write it, plus 2x1 square. So these things cancel out and you have that is equal to 0. So your values of ln gamma 1 equal to this and ln gamma 2 equal to this, these are thermodynamically consistent. So your option D is correct. So I hope you liked my teaching, and please don't forget to subscribe to my channel and hit the like button, and thanks for watching.